feeling of sort of sadness is that we now laugh, the beautiful talks on what was it, explicit and non-explicit, something like that.
It's been very explicit.
Yeah, so this is maybe not anyway. Ours certainly.
Thank you.
Yeah.
Thank you for returning. The last day of class. Thank you for folks who sent me figures and solutions. Keep them coming. I've been doing some more typing, so I've more or less written up a skeleton of everything that has happened so far. I still need to improve it a little bit, but yesterday was kind of fast and sketchy. So if you wanted to see more details of what happened yesterday, they're now in the notes. Thank you also for folks who filled out the feedback form. That was very nice. Thank you. There was one advice of something I should do today, which is take fewer questions. Sorry about that, especially since today is the last day. I think I will try to pull those through a little bit. Today we wanted to do something a little bit less explicit and more sort of, I don't know, theoretical, whatever that means. And so in particular, oh, I forgot to set my alarm. So in particular, what we wanted to prove today was the fact that Alexander polynomial one knots are topologically sliced. I should set this for 1450. With this. No, 1445. That's the count. Great. All right. So here's our goal for today. We wanted to prove this result of Friedman and Quinn. That Alexander polynomial one knots are topologically sliced. We won't really need to know very much about what the Alexander polynomial is. It will turn up eventually in the proof. And in case you haven't seen it before, you may as well take that to be the definition of Alexander polynomial one when it turns up. So don't worry so much about what this means in case you haven't seen it before. But I do want to at least remind you what the definition of topologically sliced is, just in case you haven't seen that before. So definition, a knot K is topologically sliced if, well, what is K? K is some embedding of S1 into S3. And this knot is said to be sliced. Well, S1 is the boundary of D2, S3 is the boundary of B4. And this topological sliceness means that there's a locally flat embedding here. And so in particular, pictorially, if I draw you B4 like this, the boundary is S3, my knot shows up right here. This is saying that I can fill in some disk right there. This is a locally flat embedding, so in particular, we learned that that means it has a normal bundle. So that means this extends to an embedding of D2 cross D2. So there's this, you can fill this in. In general, if you don't like to think about local flatness, you could just think that topologically sliced means I bound a disk inside of B4 that has this extends to a product neighborhood. Okay. I'm assuming most of you have at least seen this definition before in Mark's problems. He talked about ribbon knots. Ribbon knots are smoothly sliced. Not all knots that are smoothly sliced means smooth disk. Smoothly sliced implies topologically sliced, but it doesn't go the other way around. So in particular, so examples, ribbon knots are smoothly sliced. Remembering that definition from Mark's problem set, this theorem tells us that Any knot with Alexander polynomial 1 knot is topologically sliced. In particular, in case you happen to know what this is, the positive clasped white-head double of the right-handed trefoil is topologically sliced, but it is not smoothly sliced. I'm not going to go more into the details of sliceness. I'm just going to construct a disk for you. The main thing that I will use is this characterization of topological sliceness. I've been using my defense mechanism of just putting this on the homework for you to prove. And I've written that up there for you just to save time. Here's how the proof goes. And I will leave it to you to fill in the details. If I have a disk like this for my knot in B4, I could take W to be the complement in B4 of this sliced disk delta. So my W, if I have a sliced disk, can take the sliced disk complement. One of the things that Mark told us yesterday is that we can recognize the boundary of this sliced disk complement as the zero surgery. You can see the knot complement on the outside and you fill in a solid torus on the inside. Some nodding, okay. And then the forward direction of this theorem is really straightforward. You just check. The really much harder thing is to go backwards. Like you have some sliced disk, potential sliced disk complement with the right boundary. How do I now recover my original slice disk? Well, what you do is, well, you glue a disk back in. So you start with W, you attach a two-handle along the meridian of the knot. The meridian is what normally generates pi1. So when you do this, you create something simply connected. You can check that what you've created is a homotopy 4 ball, but those are homeomorphic to B4 by Friedman. And therefore that's actually a B4 you've created. And you have to check that you've made your knot topologically sliced when you did this. Especially since this is an exercise, I'm not gonna say more about that, but I hope you'll accept that if I could find a 4-manifold with these properties, then I will prove for you that my knot is sliced. And the strategy of the proof today is precisely this. My advisor used to quote the matrix at me for this strategy. This is like what we've been doing in the last 3 days. We've been trying to find the surfaces themselves. But what we're going to do today is try to find the complement of the surface. The matrix quote is, don't bend the spoon, bend the complement of the bend the space, the negative space around the spoon, whatever, something like that. That's what we're doing right now, is we're going to build the complement and then convince ourselves that it is the complement. That's kind of the idea. Okay. I will now do this, but in case that was very confusing, the thing that I have said is I will build W and that will suffice because of this theorem. So modulo this theorem, I hope it's clear what we're doing. Let's get started. Our goal is to build such a W. Well, I need to know something about the zero framed Dane surgery. What I know is that H1 of this guy is Z. That means that H upper 1 is Z, and that means that I can produce from this a function, a continuous map from this zero surgery to S1, such that this meridian, I consider the induced map on fundamental groups, This takes the meridian of my knot to the generator. Using some facts here, so H upper 1 with Z coefficients, that's the same as homotopy classes of maps to KZ1. But what is KZ1? It's S1. So you pick pick the map to S1 that corresponds to the generator. You unpack all the definitions. This is what you get. The W that we built will have the following property. So we want I have this map F to S1. My W will be the thing of which a thing with that boundary. And I'll set it up so that there's a map from W to S1, such that this diagram commutes, such that this is a homotopy equivalence. This is the thing that we will do. We haven't done it. The entire point of the proof is to do that. What I hope you will believe is that if I do this, I will satisfy the conditions in my theorem, and that will be enough. So this applies the conditions on W in my characterization. So if I do this, P will be topologically sliced. So W should be compact connect format. It's a homotopy equivalence, so H2 is 0. Pi 1, the meridian stuff, that just comes from commuting. You can check that. All right, so this, if I do this, then I win. How will I do this? We'll do this in steps. So I want to build the right kind of four manifold with boundary, the zero surgery. Well, let me start with any four manifold with boundary, the zero surgery. And then I'll try to fix it up somehow. Okay, so that's the idea. So let's start by considering, I'm going to write something down. It will not be what you're expecting, perhaps. This is the three-dimensional spin Fordism group over S1. So what the heck is this? You may have seen this without this parameter. That would just be spin three manifolds modulo spin Fordism. What that means is that you take everything with a map to S1. Okay, so elements of this group are three manifolds with a spin structure with a map to S1. And two such dudes are equal. There's a spin four manifold in between, also with a map to S1, restricting to the right things on the boundary. So the thing that you have seen without this argument is the thing over a point. Does that make sense? Because you always get maps to points, mapping everything to a point. So it's like having the extra map to a point is pointless. But this sort of makes it a richer structure. This is a generalized cohomology theory, WTF. And in particular, this means I know how to compute this using some spectral sequence. And as a result, you can use that to compute that this is Z mod 2. That is a black box. I don't want to open it. But people know how to do this stuff. You are confused why I'm using the word spin, but you'll see why it comes up later. Seems to be coming out of nowhere. Daniel doesn't think so, but I personally thought it was like coming out of nowhere. So if you also feel this way, I know where you're coming from. What do? Well, I consider I have this three manifold. It has a spin structure. It has two, in fact, but take either one of them, don't care. And you want to consider that thing in this group So consider here S30 arbitrary spin structure. I have this isomorphism. I know precisely where this element maps to. Turns out that this element maps precisely to the ARF invariant of K. If you haven't seen what that is, the only thing you need to know is that if your knot has Alexander polynomial 1, then its ARF invariant is trivial. So in particular, and the spin structure did not matter. And so in particular, this thing is the boundary of some spin for manifold with a map to S1. So this is just a fact. And a fact. And so that implies that I've built for you my original map. And I have this V. It's not a homotopy equivalence yet. I have at least some four manifold that I can work with. Call this F prime. So now I have an actual four manifold, and I have a map to S1. I want a four manifold with a map to S1 where that map is a homotopy equivalence. So the helpful factor is that I have something to work with, so I can try to mess with it to make it into a homotopy equivalence. And I'm going to mess with it by doing what is called surgery. Yes?
You are not going to get a homotopy equivalent in the end, no, right? Because it's pi 1 is not Z.
Yeah.
Pi 1 of W.
But this one's pi is also not zero.
I mean, in that theorem, maybe you get pi 1 Z. Okay.
That's right. So what Chu is pointing out is that if I succeed, not only will I build a slice disk, I'll build a slice disk with pi 1 Z in the complement.
Okay.
So that I'm doing something more than you needed me to. Does that make sense? But you're absolutely right that if I succeed, what I'm saying is that the slice disk complement will have pi 1 Z. Okay. But that's not a contradiction.
Mm-hmm.
Z is normally generated by its generator.
Sir, I think I missed the part that you did this V4 is constructible because the unknot is like at the trivial one has alpha invariant 0. So you're actually building for this and you fill in. So
I'm just saying that my knot K has Alexander polynomial 1. And that means my knot K has ARF invariant trivial. And then my knot's zeroth frame surgery, maybe that's what you meant by trivial 1. But I'm saying that this thing maps to the trivial thing in this Fordism group. And that means that there's a four manifold that I can put over by the definition of what this group is. It was an O moment. That's good.
I mean, without the map, it's easy to find such a W, right?
That's
You
right.
take the two-handle attachment, but you cannot extend the map.
The map to S1 is very important because that is the thing that I'm trying to fix up. Yeah.
Does gauging Alexander polynomial 1 come into like the surgery bit, like when you're doing the map to star, or does he?
No, this is a fact about this isomorphism.
I think he's asking if the original theorem we're trying to prove is true for all ARF invariant 0 knots.
You will use the Alexander polynomial 1 condition in a moment. We haven't used it yet. So far, all of this would have worked for ARF invariant 0 knots. And in particular, I think you could use this as a definition of what it means for a knot to have ARF invariant 0s. That would be a weird definition, but you could do that. Okay, now I will self-censor and move on. Sorry, ask me questions later. Oh, it's weird. All right, so plan. Modify F prime to a homotopy equivalence, F prime and V to a homotopy equivalence. By that I mean like my four manifold will change. Consequently, the map will change. See, like in the following very precise way. Well, you have to recall Whitehead's theorem that if you knew that F prime star, if you knew that this is an isomorphism for all I, that implies that F is a homotopy equivalence prime. These are nice CW complexes. I have an honest to goodness map. Whitehead's theorem says the thing that I've written down. Okay. Not going to go into the details of the next thing, but like by Poincare-Lefschetz duality, basically, for us, it will suffice to check I equal to 1 and 2. Also 0, but okay. So this means if I could do some modification to make F star an isomorphism on pi 1 and on pi 2, then I'd win. Apparently that's one of the things I say. But that's my win condition. Okay, that's what I need to set up. I might be going too fast. Super weird. Great. All right, so how will we fix up I equal to 1? Because of where our F came from, like this map was like very nice on pi 1. This means that F star on pi 1, prime star, sorry, all of these are primes, is already a surjection. You believe that, right? I can't possibly have been mapping to 1 if it weren't a surjection. Yeah. So I want to make it an isomorphism. So I need to kill the kernel somehow. Make sense? So I'm going to kill the kernel by I don't know why I'm writing it this way. Kill kernel by surgery on circles. This is another thing that I've put in your homework, but let me tell you what it is. So if you have a circle, gamma, inside of your four manifold, surgery on that circle means the following. Hope that you started off with an orientation preserving circle, because, come on. And then notice that means it has a tubular neighborhood, which is an S1 cross D3. I'm going to cut it out. It leaves behind an S1 cross S2 boundary. And I'm going to glue in a D2 cross S2 to kill it. There might be some choices, depending on how you identified that S1 cross D3. You will consider this in your exercise. But the main point is that that D2 that you're gluing in, that D2 has boundary that S1. I'm informing you that that is how you'll glue it in. And so in particular, whatever that gamma was, you have made for it a null homotopy because you gave it the disk for it to bound. Yeah. So surgery on a circle kills it in pi 1. You believe that, right? Yeah. And in particular, you could kill a kernel by doing this, by taking, well, the kernel is some subgroup of pi 1, represent all of those by circles, embedded circles, orientation preserving circles, do surgery. When you do this, you will have an isomorphism on pi 1, right? In fact, you'll have a little bit more. So I have this V, right? And I'm messing with this F prime, but I still need the map to S1, right? I can't just modify my four manifold without losing that map. The map is the whole goal. So what we notice is I have this V, and it had this map V prime to S1. When I do surgery, I'm going to call it V double prime because I'm going to have this map F double prime there. And the reason I have this map F double prime is because there is a cobordism from V to V double prime. And there's a map that comes from the entire cobordism. And the way to think about this is that you affect this surgery by adding a handle, a two handle specifically. And you have to extend this map F prime over that two handle. Why can you do that? Well, the thing that you attach the two handle to, it maps trivially over to S1 because it was in a kernel. That's exactly what you need in order to extend. So you get this extension on the level of the four manifold, five manifold. So Andres talked about potatoes. So mine are always these ZB, rigatonis, whatever. And then these are always four-dimensional, right? Just does anyway. And this is a five manifold. You get this map on the five manifold, so you get it on its boundary. Okay, so now you've fixed up the one case. Now you're almost done. You just have to fix up two, right? And if you're done with that, then you'll be done. And what you want to do is something very similar. You could look at the map on pi 2. Well, S1 doesn't have any pi 2. So you're trying, whatever your V double prime is, you just want to kill all of its pi 2. The key thing that I needed here was that my circle was embedded. Because in a circle in a four manifold, I can always do that. But for pi 2, I'll have spheres in a four manifold, and embedding those is really, really hard. That's why we're all here. And that's where Friedman will come in and save us, basically. But do you all agree that if we could we could set it up to be an iso on pi 2 without messing up what we've already done, then we would. Okay. Now I will actually ask, are there any questions? The next step is like the key step, but let's make sure we're all on the same page before that happens. Yes.
Sorry, what if by proper left chest duality we check?
Yeah, I will not answer that. But the reason I will not answer that is like, the point is that if you have an isomorphism on 1 and 2, then I'm claiming that by using the correct type of duality, we'll get an isomorphism on 3 and 4. This is not really clear because these are pi's, not h's. But they are h's if you consider them with twisted coefficients. And you consider them with, there is a Poincare duality, Lafschetz duality with those twisted coefficients. You have to sort of work that out, that I don't want to talk about. But please accept that as a black box. I promise it works. Usually you would do this with a closed manifold and things would be easier. The fact we're working with the thing with the boundary makes it more annoying. I can point you to some nice references if you would. That's a good question. Yeah?
Is the cylinder a cobordism or a bordism over S1?
It's a bordism, it's a cobordism over S1. I don't know if the co versus lac made a difference, but like the fact that there's this map to S1, that's what means it is over S1. Does that make sense? So the point was that this 5 manifold does have that map. That was kind of how I built it. So I now have this anachronistic, but that's what we have.
Spinness is not an issue anymore.
We will use it in a second in a way that I will black box. But
So
you should convince yourself that it is spin, and in particular, you should choose the right framing to make it spin.
So we are still worried about this fish.
Well, I'm trying to not let you think about it too much, but yes, you should. You should.
Doing zero surgery?
Should use the spin framing, and I think that is the zero. But like the spin sort of gives you the framing. Any questions? Now the Friedman thing will come in. The Friedman-Quinn thing will come in. All right, so I want to kill I2. Not just the kernel anymore because it's mapping to the trivial group. So I just want to kill it. And in order to do so, I'm going to need some help. And what I'll need will come from algebra. So I'm going to consider this triple. This will be pi2 of v double prime, comma lambda v double prime, and mu of v double prime. These guys are those equivariant intersection and self-intersection things that you saw in your exercises. Don't want to go into that too much, but like in particular, this lambda was a form on pi2, right? So we saw that this gives, so this one in particular took two elements of pi2 and spit out an element in z pi1. So in particular, this is, I always have to remind myself of what this is. So here, what we're using is that lambda is a sesquilinear Hermitian non-singular bilinear form. And then mu is a quadratic refinement for it. I will certainly not tell you what any of these words mean. Feel free to look them up on your own. I will point to this word, non-singular, because that is precisely where we need the Alexander polynomial 1 condition. So why is this non-singular? It's non-singular because H1 of the zero frame surgery with z of z coefficients, this is trivial. What the hell is that? That is equivalent to Alexander polynomial 1. Okay, so this thing, again, it would be a weird definition. You could take this to be the definition of Alexander polynomial 1. I'm going to spend 2 sentences talking about this. What is this? This is some homology with twisted coefficients. That z is the meridian. Just literally by definition, in case you haven't seen homology with twisted coefficients, which is normal not to have seen that necessarily. By definition, what this says is, this is my zero frame surgery. It has a map to Z. That means it has a covering space, which has Z as the deck group. So that means that covering space, if I take its first homology, it has the action of the integers on it. So by definition, this item is H1 of that infinite cyclic cover, considered as a module over Z adjoined meridian, where the meridian acts by this deck group. This is more geometric than it might seem at first glance. The Alexander polynomial, by definition, this thing is called the Alexander module of the knot. By definition, the Alexander polynomial is the order of the Alexander module. An order means like order like in the case of a finite group. Like a finite group's order is the number of elements in it. Alexander polynomial 1 means the order of the module is 1, which means that it's trivial. I should have said 0, sorry. Should have said trivial. All right, but there's a lot of knot theory wrapped up in one short sentence. The point is that these are equivalent. Please accept that as a black box in case you have not seen that before. And now you might think, well, okay, fine, I'll take that, but why is that related to that being non-singular? That's some intersection form in the four manifold. That four manifold has this thing as a boundary. And this is also being considered in Z of Z coefficients, because Z is my pi1 right now, right? Pi1 of V double prime is Z. So these guys have, these have values in Z of Z. That was my definition of the equivariant intersection number. And you should think about this as like, when do you know the intersection form? The plain old integer intersection form of a four manifold is given by an invertible matrix, where the boundary has to be a homology sphere. Think about like the relative homology sequence of a pair. The long exact sequence in homology of a pair. So you'll get this one, and then H1, H2 of this second one. These guys are 0. Some map is an iso. That map being an iso in that long sequence, that's the same as it being non-singular. That's literally the definition. So if you know that a four manifold has non-singular intersection form, integer intersection form if its boundary is a homology sphere, this is the pi1 version of that. I'm not going fast after all. Everything's very slow. All right. Have I lost all of you or only some of you? None of you. Some of you. All right. There's this gadget. The gadget has a nice form, form in a non-technical sense. This is a nice item. That's what the Alexander polynomial condition gives me. And in particular, it means that I can consider it in this gadget called L4. L4 by definition is the group of these items. And people, not us, algebraists, have studied these things. Okay? This thing is well understood. Not by us, but by someone. And thankfully, they have computed these things for us. So there are a few things that you need to know about this group. And I'm going to write it down. And that's all. That is all you need to know. This group has these elements. Z pi 1 module, form on it, quadratic enhancement. It's these considered modulo so-called hyperbolic forms. So hyperbolic forms means, i.e. those that look like this. I'm going to put scare quotes on here because it's not literally that, whatever that means. But a hyperbolic matrix is one that looks like this. And a hyperbolic form is roughly something that looks like this. There will be a half-dimensional submodule on which all of the lambdas are 0. By definition, all the mu's will be 0. There's some standard hyperbolic thing that you mod out by. And that L4, by definition, is these guys modulo these forms. That's what makes it easy to understand. If you don't mod out by this thing, it becomes horribly complicated, even for algebraists. Okay. So we like the fact that we mod out by hyperbolic forms. You'll see why in a second.
Again, what's the quadratic refinement?
I will not because I did not tell you.
Oh,
Quadratic refinement means it's just an additional thing that behaves well with lambda. It has a bunch of properties. It says it's like mu of A plus B equals mu of A plus mu of B bar plus lambda of AB, something like this. It's this additional algebraic gadget. I don't want to talk about it. It's not important, is maybe the better answer. All right, the other fact that you need to know about it is that this is well understood In particular, this is isomorphic to 8 times Z. And it's generated by the E8 form. Whatever that is. The E8 in the E8 manifold E8 form. And this thing maps to the Z via the signature. This is just don't think about it too much. Otherwise, don't worry about it too much. It's just, we happen to know what this is.
What is L4? L4 is,
This is isomorphic.
I mean, what is the L4?
Some groups.
What's the definition of
L4.
L4?
The definition of L4 is, it is called the L group. L stands for L. And it's a type of which group? By definition, it's the group whose elements are Z pi 1 module. This is the Z pi 1. Z of Z module with the sesquilinear Hermitian non-singular bilinear form on it, comma, quadratic refinement, mod out by these. That is the definition. You don't need to know the definition though. All you need to know is that it is isomorphic to 8Z, and its generator is well known. The next fact you need to know, it's not an algebra fact, is that there exists a closed topological form manifold called the E8 manifold, whose intersection form is the E8 form. This looks like a tautology, but this was constructed by Friedman. And so in particular, I could take my V double prime, I consider this thing on it, and I see what it is in L4. It will be something in 8Z, some 824, 8 times 1 billion. There will be some element here. But I know something which maps to the generator. So I could consider, I had my V double prime to S1. I could consider the connected sum with some number of copies of that E8 manifold. So that now this guy, I choose my N so that for him, the map to 8Z is actually trivial. Do you know what I'm saying? So if V double prime was mapping to 16, then you should have taken minus 2 E8s. And this connected sum will now map to 0. What you have to convince yourself of is that there's a Bordism here, so that's not too surprising. And in particular, this map extends. So you get a map to S1 still. I'm not going to talk about it. You get this? We do this connected sum. That map is now trivial when considered in L4. You're like, why am I doing any of this? What this means is if I now consider, instead of V double prime, I consider this new guy, this triple in L4 will be 0. What does 0 mean? It means it's a hyperbolic form. What does it mean to be a hyperbolic form? So this guy now has hyperbolic form. That means that there's a half-dimensional submodule on which lambda vanishes, on which mu is 0. And there's another half-dimensional submanifold, which is algebraically dual to it. So it means I have precisely these classes in pi2 that pair up so nicely. So in particular, this means, by literally thinking about the definition, it means that in the nicest case, there exists F and G, generic immersions of S2, mapping into V triple prime, such that mu of f equals mu of g equal to 0, and lambda of fg is equal to 1, and they have trivial normal bundles. That's where the spin comes in, Andras. It's like you control this bundle stuff. That's why we did that. We're so close, you guys, so close. That should look familiar. That's the input to the sphere embedding theorem, which is another thing in your exercises. One holdup is not in a simply connected manifold, but that's okay. I'm in a pi1z manifold, and I do have a sphere embedding theorem there as well. So now apply a sphere embedding theorem with pi1z to this collection to produce f bar homotopic to f, g bar homotopic to g, such that f bar is a locally flat embedding, and f bar intersect g bar is a single point. That was the hardest step. 1 second. Okay. Now we're basically done. I wanted to kill all of pi2. In reality, pi2 is probably big. It has like 2 times 75 elements. Then I would have 75 Fs and 75 Gs. But it'd still be some finite collection, and I have a finite sphere embedding theorem. Then I've embedded half of my pi2. Now I'm going to do surgery. So do surgery. My alarm didn't go off, I don't know why, on this f bar. So what that means is I'm going to take this v triple prime. I'm going to remove f bar cross d2. It's a trivial normal bundle guy, so it's an s2 cross d2, and I'm going to glue in a d3 cross s1. You have to convince yourself that if I do this surgery, not only do I kill f bar, I also kill g bar. That's like if you're on a torus and you cut along the meridian and glue, it also kills the longitude because you like destroyed part of the longitude. It's like not there anymore. So you have to convince yourself that when you do this, you have killed all of pi2. And you also have to convince yourself, that you already did this before, is that this not only describes a modification, this also describes a cobordism that goes from v triple prime to the result. So you had v triple prime with a map to S1. And then there's this cobordism, still tubular, that produces for you what I will call W. And that will still have this map to S1, but you have now fixed it so that this map, FW, is an iso on pi1, is an iso on pi2, and therefore is a homotopy equivalence. That's the end of the proof. I have 1 minute. I still want to tell you something, so I'm going to take a little bit of time to do that. No, let me not do that. Just going to tell you things verbally. I'm sorry, someone. I'm going to just make you wait until the very end. Today was very different from the last 3 days, right? Right? At least to me, it was very different. These are both the sorts of arguments that we have in topological four manifolds. There are things where we do things very explicitly and directly. There are things where we sort of this is, at least to me, not at all explicit. You have to learn about L groups. You have to learn about like Bordism groups. There's some spectral sequences. It's much more algebraic. Somehow this is like a feature of topological form manifolds, is that they can be controlled algebraically, but it's very powerful. But they are very different. And so if there's a few things that I would like you to take away from these 4 lectures, it's the following. The first is that not everything in topological form manifolds is super abstract, super fractally. It can be very explicit. You can draw lots of pictures. Things can be very geometric. Other thing I would like you to take away is that, I mean, the result I talked about in the past 3 lectures, well, it's from 97, but the proof that I gave you was from 2022. This thing that I talked about today, this is from the late 80s. I was going to write down new results that were done using surgery theory, new results that come from the last few years. Instead of writing that down, let me just point you to Tuesday. At least Patrick Orson will talk about using surgery to classify RP2s inside of S4. So the other thing I want you to take away from this is like new results exist in the topological category. And so you too could be coming up with new results in the topological setting. And it's not like, it's completely reasonable and accessible to do that. Final thing that I wanted to say is, I'm sorry I never made it to showing that Pi1Z2 knots are topologically unknotted. But Daniel has very kindly volunteered to give a short talk on that in the TA session. So if you're interested in hearing that, please do come to the TA session. Maybe that will be the beginning. Yeah. And then finally, thank you so much. Thank you so much for participating. It's been so fun. Someone had a question.
So you never mentioned about the Pi1 of EA.
I did mention the Pi1 of E8. Thank you. That's very important. It went away, but it's simply connected.
Yeah,
That's very important.
And speed.
And spin. I also didn't tell you why this G bar is important. But it is. So please consider why the G bar is important. Any questions?
So the spin cobordism was only used at the first time. Is it used throughout? The spin condition is important throughout, or only at the first time?
I did not talk too much about the spinness, but the spinness was important for the mu. I did not talk about this. I should have, but it's sort of every time that we were doing these surgeries, whenever we were thinking about this mu is not a regular. One of the things you learned in the exercises is that mu is not something defined on Pi2, because you can change, like if you do a little cusp homotopy, it changes mu. So what the spin condition in addition gives you is it fixes a regular homotopy class.
I see.
And that's why mu is something that actually makes sense. So there are things that you have to be careful about. It's very sketchy and I didn't do it. But it's there. It shows up in multiple places. And in particular, it's the mu's and the framings where it comes in.
So the cobordisms are always constructed to be spin.
That's right. So in the 3-manifold case, spin is what you need. In the case that your boundary is a 3-manifold, you're doing this rel boundary. What am I trying to say? Right, because you started off with this boundary 3-manifold. Spin is sort of more than you need, is what I'm trying to say. There is, like what I did today was surgery. These are called surgeries, but you can package this up very systematically in something called the surgery exact sequence. And in there, usually what you consider are not spin bordisms, but normal bordisms. And that's like you sort of keep track of something on the stable normal bundle. And that's what plays the role of whatever spin did for us here. So spin is easier for us to understand because it's something we see in 4 manifolds. But the natural thing that occurs in surgery is these so-called normal vorticisms instead. It's a long answer, but I hope that helps. But there's always like, you want to keep track of something at the bundle level, and that specifies your spheres for you and framings for you, as you might expect. Yes.
Why did you get the trivial normal bundles?
The trivial normal bundles kind of come from, it's not here. It's like, it's part of the, it's gonna give you a fake answer. It's like part of what it means to be hyperbolic. Like the lambdas are 0, the mu's are 0, and we had that formula of lambda and mu. That implies that the E is trivial, do you remember? We had this formula.
So maybe the right question should have been why mu at 0.
That was, I cleverly did not write this down. I wrote down the hyperbolic form is that matrix. That matrix only records the lambdas. I should have told you what mu is. And mu is 0.
I see.
That's the definition of hyperbolic form. I should have given you a module and the lambda and the mu. The mu is 0. It's not a satisfactory answer. But like that is the thing, the 0 thing in L4 has the 0. Sorry. We wrote a long chapter about surgery theory in dimension 4 in the disk embedding theorem book. So if you want to know more about that, that chapter might be useful. Oh, and in fact, I wanted to advertise, maybe you already saw in the Discord, that there might be a group of people planning to read a textbook about the disk embedding theorem. So if you're interested in doing that, get in touch with Ikai. Is that, or join the Discord thing. The Discord that is advertised in the Discord. Discord inception. All right, thank you so much.